Somewhere in the deep silence of space, long before Earth had oceans, before the sun had light, before time meant anything to anyone, there was only a drifting cloud. It moved slowly through a quiet region of the galaxy we now call the Milky Way, a vast spiral of stars turning gently in the dark. This cloud was enormous beyond imagination, made of cold hydrogen gas, faint traces of helium, and tiny particles of ancient stardust left behind by stars that had already lived and died. It was not dramatic. It did not glow brightly. It simply existed, suspended in cosmic stillness, waiting without knowing it was waiting. For millions of years, nothing seemed to change. The cloud remained diffuse and calm, stretching across light years like a barely visible mist. But space is never completely still. A distant supernova, the explosive death of a massive star, may have sent a ripple through this region, a soft but powerful wave of energy that gently disturbed the cloud's balance. Or perhaps gravity, patient and persistent, simply began its slow work. Either way, something shifted. The cloud began to contract. As it shrank, it spun. Not quickly at first, just a slow, graceful turning. But as gravity pulled more material inward, the rotation increased, like a figure skater drawing in their arms. The center of the cloud grew denser, warmer, brighter. Pressure built quietly, steadily, over hundreds of thousands of years. The temperature rose from freezing cold to thousands of degrees. At the heart of this spinning disk, a newborn star began to form. This young star would one day be known as the Sun, but at that time it was only a glowing sphere of collapsing gas, not yet shining with the stable light we recognize today. Around it, the remaining material flattened into a wide rotating disk, like a cosmic vinyl record made of gas and dust. This was the protoplanetary disk, the cradle of everything that would follow. Within this disk, tiny particles of dust began to collide. At first, they were microscopic grains, bumping into one another softly, sticking together through static forces and gentle attraction. Over time, these clumps grew larger. Pebbles became rocks. Rocks merged into boulders. Boulders collided and formed mountain-sized bodies drifting through the disk. The process was chaotic but strangely calm on the grand scale. Collisions happened over millions of years, each impact shaping the future in slow motion. Gravity guided everything. Larger bodies attracted smaller ones. Slowly, gradually, the early building blocks of planets, called planetesimals, formed. They orbited the young sun in slightly different paths, sometimes merging peacefully, sometimes crashing together in violent bursts of heat and light. But even those collisions were part of creation. Out of destruction came growth. Closer to the sun, where temperatures were intense, only metals and rocky materials could survive. Here, the inner planets began forming dense, solid worlds built from iron and silicate rock. Farther away, beyond the region where water could freeze into ice, giant planets started to take shape. Ice, gas, and dust combined into enormous cores that pulled in vast atmospheres of hydrogen and helium. The architecture of our solar system was slowly emerging. As the sun's core became hot enough, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing immense energy. Light burst outward for the first time. The sun began to shine. Solar winds, powerful streams of charged particles, flowed across the disk, sweeping away leftover gas and dust. What remained were the planets, moons, asteroids, and comets that would orbit this star for billions of years. In this early time, the solar system was not peaceful. It was a place of constant impacts and shifting orbits. Young planets were molten, glowing with internal heat. Asteroids rained down in what scientists call the late heavy bombardment, reshaping surfaces again and again. But even this chaos was temporary. Slowly, over hundreds of millions of years, things began to settle. The inner rocky worlds cooled. Crust formed. Volcanoes erupted. Atmospheres thickened. Farther out, the giant planets stabilized their positions, their immense gravity shaping the structure of the entire system. One of them, Jupiter, became a kind of cosmic guardian, its powerful gravity deflecting many wandering asteroids and comets, influencing the safety and evolution of the inner planets. Beyond the outer planets, icy remnants remain scattered in distant regions, silent witnesses to the solar system's birth. Some would occasionally journey inward, becoming comets with glowing tails, briefly illuminating the darkness before returning to the deep freeze. And at the center of it all, the sun continued to shine steadily, balancing gravity pulling inward with fusion pushing outward, creating a stable warmth that would one day make life possible on a small blue world. If you could watch this entire story unfold from beginning to end, it would not feel rushed or dramatic. It would feel slow, almost meditative. The formation of a solar system is not an explosion of constant action, but a gradual dance of gravity, time, and patience. Millions of years pass like soft breaths. Matter gathers. Heat rises. Light is born. Tonight, as you imagine this ancient cloud drifting quietly in the Milky Way, slowly collapsing into something bright and enduring, allow yourself to feel that same gentle sense of becoming. Everything around us, the ground beneath your feet, the air you breathe, even the atoms in your body, began in that swirling disk of dust and fire. We are not separate from this story. We are its continuation. And as the newborn sun glows softly in the vast dark, surrounded by the early shapes of worlds still forming, the stage is set. The planets are not yet what they will become. Oceans do not yet exist. Rings are still gathering. Moons are still colliding into place. The solar system is young, warm, and full of possibility. If you drift inward now, closer to the warm brilliance of the sun, past the region where the young solar winds once cleared the remaining dust, you will find a small, quiet world circling in tight devotion. It moves swiftly, almost nervously, tracing a narrow path around the light that gives it existence. This is Mercury, the smallest of the 8 planets, and the one that lives closest to the sun's steady fire. From a distance, Mercury appears modest, even fragile, a gray, cratered sphere reflecting sunlight in sharp flashes. But proximity to the sun shapes everything about this world. Its year is short, lasting only 88 Earth days, because it orbits so close. Yet its day, the time it takes to rotate once on its axis, is strangely long. Mercury turns slowly, caught in a gentle gravitational rhythm with the sun known as a 3:2 spin-orbit resonance. For every 2 orbits it completes, it rotates exactly 3 times. This creates a pattern in its sky that would feel unfamiliar and mesmerizing. Imagine standing on Mercury's surface. The sun would appear enormous, more than twice as wide as it looks from Earth. At certain moments, due to the planet's elliptical orbit, the sun would seem to pause in the sky, move backward briefly, then continue forward again. It would be a silent celestial ballet, a slow-motion dance between gravity and motion, repeating over and over through endless cycles. Mercury has almost no atmosphere to soften the sun's heat. During its long daylight hours, temperatures soar to around 430 degrees Celsius, hot enough to melt lead. Yet when night falls and the sun's warmth disappears into the black sky, temperatures plunge to minus 180 degrees Celsius. It is a world of extremes, where heat and cold exist side by side, separated only by the thin line of sunrise or sunset. And yet, despite these harsh conditions, Mercury is not entirely lifeless in character. Its surface tells a story written in craters and cliffs. Billions of years ago, during the early solar system's chaotic youth, asteroids struck Mercury again and again. Without a thick atmosphere to burn them away, these impacts scarred the planet permanently. One of the largest of these scars is the Caloris Basin, a massive impact crater stretching over 1,500 kilometers across. When the asteroid struck, the shockwaves traveled through the entire planet, reshaping the terrain on the opposite side. Even today, the surface bears wrinkles, enormous cliffs called scarps, formed as the planet slowly cooled and contracted over time. Unlike Earth, Mercury's interior cooled quickly due to its small size. But it still retains a large metallic core, rich in iron, taking up a significant portion of the planet's volume. This oversized core creates a magnetic field, weak compared to Earth's, but present nonetheless. It is a quiet reminder that even small worlds can hold powerful secrets beneath their surfaces. From space, Mercury's color palette is subtle. Soft grays and faint browns blend together under the sharp sunlight. There are no clouds drifting overhead, no winds shaping dunes, no oceans reflecting the sky. Silence dominates here. If you could stand on Mercury, there would be no sound at all, because sound requires air to travel. Only the distant, blinding sun would hang above, radiant and constant. Yet Mercury is not entirely alone. Occasionally, it passes directly between Earth and the Sun in an event called a transit. During such moments, observers on Earth can see a tiny black dot slowly crossing the Sun's bright disk. It is a delicate sight, a reminder of the precise geometry that governs planetary motion. The study of Mercury required patience from humanity as well. For centuries, it was difficult to observe clearly because it never strays far from the Sun in our sky. It appears briefly during twilight, either just after sunset or before sunrise, then vanishes again into the glare. Only with space missions did we truly begin to understand it. NASA's Mariner 10 was the first spacecraft to visit Mercury in the 1970s, revealing a heavily cratered surface similar to Earth's moon. Decades later, the Messenger mission orbited the planet, mapping it in extraordinary detail and uncovering evidence of water ice hidden in permanently shadowed craters near its poles. Yes, even here, on the planet closest to the Sun, water ice exists. In deep craters where sunlight never reaches, temperatures remain cold enough for ice to survive. It rests quietly in darkness, untouched by the blazing heat only a few kilometers away. This contrast feels almost poetic, fire and ice sharing the same small world. Mercury teaches us something gentle about resilience. Though it endures intense radiation, extreme temperature swings, and constant solar wind, it continues its orbit faithfully, unhurried and precise. It does not rush. It does not falter. It simply follows the path carved for it by gravity billions of years ago. As you imagine Mercury gliding silently around the Sun tonight, picture the vast emptiness around it. No atmosphere to scatter light into soft colors. No weather to stir movement. Just stark sunlight and long shadows stretching across ancient craters. The Sun rises slowly, climbs high into a pitch-black sky, and sets again over a horizon unchanged for eons. This is the innermost guardian of the solar system's rocky worlds. Small, enduring, and quietly extraordinary. And beyond Mercury's swift orbit, another world waits, wrapped not in silence but in clouds thick and luminous, glowing softly like a pearl in the morning sky. As we drift outward from the swift orbit of Mercury, leaving behind its sharp sunlight and silent craters, another world begins to glow ahead of us. It does not reveal its surface easily. Instead, it shines with a soft, creamy brilliance, wrapped completely in layers of cloud. From Earth, it is often the brightest object in the sky after the Sun and the Moon, appearing gently at dawn or dusk. Ancient civilizations watched it carefully, believing it to be two different stars, one heralding morning, the other guiding evening. This luminous world is Venus, sometimes called Earth's twin, though in truth it is a twin shaped by very different choices of nature. At first glance, Venus and Earth seem similar. They are nearly the same size. Their masses are comparable. They formed from similar materials in the same early solar disk. If you could hold both planets side by side in your imagination, they would appear almost like siblings born of the same cosmic moment. But beneath Venus's bright clouds lies a world transformed by heat and time. Those clouds, thick and swirling, are not made of water vapor. They are composed largely of carbon dioxide gas and droplets of sulfuric acid. They form a dense atmosphere that traps heat with extraordinary efficiency. This is the runaway greenhouse effect in its most dramatic form. Sunlight passes through the upper clouds and warms the surface below, but the heat cannot escape back into space. It builds and builds, layer upon layer, until the planet becomes hotter than Mercury, even though it is farther from the Sun. If you could descend slowly through Venus's clouds, the light would fade from golden brightness to a dim, yellowish glow. The air would grow heavier, thicker, pressing against you with increasing force. By the time you reached the surface, the atmospheric pressure would be more than 90 times that of Earth's, equivalent to being nearly a kilometer underwater on our planet. And the temperature would hover around 470 degrees Celsius, hot enough to melt lead, hot enough to erase the distinction between day and night. Yet Venus rotates in a way that feels almost dreamlike. It turns very slowly, taking about 243 Earth days to complete a single rotation. Even more unusual, it spins in the opposite direction of most planets in the solar system. On Venus, the sun would rise in the west and set in the east. And because its rotation is so slow, a single Venusian day, from one sunrise to the next, lasts longer than its entire year. Despite its harshness, Venus is not a barren rock in the way Mercury is. Beneath the thick clouds lies a landscape shaped by volcanic forces. Vast plains stretch across its surface, punctuated by towering volcanoes and wide lava flows frozen in time. One of its largest volcanic features, Mons, rises high above the surrounding terrain, a silent reminder that Venus may still be geologically active even today. Scientists continue to search for subtle signs of ongoing eruptions hidden beneath the clouds. For centuries, Venus's bright appearance inspired romance and mythology. The ancient Romans named it after their goddess of love and beauty. But the true nature of Venus remained hidden until the space age. When early probes from the Soviet Venera program descended through its atmosphere in the 1970s and 1980s, they transmitted the first images from the surface. The pictures revealed a rocky, orange-tinted landscape under a dim sky, scattered with angular stones and volcanic formations. Each probe survived only a short time before the intense heat and pressure overwhelmed its systems. Their brief transmissions felt like whispered messages from a world determined to keep its secrets. And yet, there is something strangely calming about Venus's permanence. Its thick atmosphere erases small craters quickly, meaning its surface is relatively young compared to Mercury or our Moon. Some scientists believe that Venus may have experienced a global resurfacing event hundreds of millions of years ago, when vast amounts of lava flooded the planet and reshaped it almost entirely. If true, it means Venus has reinvented itself in dramatic silence. High above the surface, in the upper layers of its atmosphere, conditions become surprisingly moderate. Temperatures and pressures there are not unlike those on Earth. Some researchers have even imagined the possibility of floating habitats suspended within Venus's clouds, drifting peacefully in the gentle winds. It is a curious thought that above a world so hostile below, there might exist a region almost comfortable. From space, Venus's cloud tops swirl in graceful patterns. Strong winds circle the planet rapidly, completing a full rotation in just 4 Earth days, far faster than the planet itself turns. This phenomenon, known as superrotation, remains one of Venus's enduring mysteries. Why does the atmosphere move so swiftly compared to the solid world beneath it? The answer lies in complex interactions between solar heating, planetary rotation, and atmospheric dynamics, a delicate balance still being studied. As you imagine Venus tonight, picture it glowing softly in twilight, a steady beacon near the horizon. It does not flicker like distant stars because it is close, a neighboring world wrapped in brilliance. Through a telescope, you would see phases, just like the moon's, as Venus orbits the sun inside Earth's path. Sometimes it appears as a slender crescent, sometimes as a bright half-circle, always shrouded in cloud. Venus reminds us that similarity in size does not guarantee similarity in destiny. Two planets can begin with the same materials and evolve into entirely different worlds. One becomes blue and alive. The other becomes a furnace hidden beneath clouds. And yet, there is no judgment in this difference. Venus simply followed the path shaped by its atmosphere and proximity to the sun. It spins slowly, wrapped in golden haze, reflecting sunlight back into space like a polished mirror. Beyond Venus's glowing veil lies a world you know intimately, a world of oceans and clouds, forests and quiet nights under the stars. As we drift gently outward from the glowing veil of Venus, the darkness ahead begins to shimmer with a different kind of light. Not the harsh glare of reflected sunlight, not the thick golden glow of cloud-covered skies, but something softer, a faint blue radiance, delicate and alive, suspended like a jewel against the vast black canvas of space. This is Earth, our home, though from a distance it looks almost impossibly small. From far away, Earth does not reveal its cities or mountains. It does not show borders or voices or movement. It appears as a swirling sphere of white clouds drifting over deep blue oceans and subtle brown continents. Light reflects off its atmosphere in a thin glowing line along the edge, a fragile halo of air only a few hundred kilometers thick. Everything you have ever known exists beneath that narrow veil. Earth formed from the same rotating disk of dust and rock that shaped Mercury and Venus. In its earliest days, it too was molten, its surface a sea of fire. Asteroids collided with it relentlessly, delivering both destruction and possibility. One of those impacts, involving a Mars-sized body often called Theia, is believed to have created our moon. Debris from the collision gathered in orbit and slowly coalesced into the pale companion that now circles us faithfully. The presence of the moon would become one of the most stabilizing influences in Earth's long history. As the planet cooled, something extraordinary happened. Water vapor condensed into rain. Rain fell for thousands of years, filling basins and carving valleys. Oceans formed. These vast bodies of liquid water became Earth's defining feature. From space, they dominate the view, reflecting sunlight in shimmering patterns. Water regulates temperature, shapes climate, and ultimately made life possible. Unlike Venus, Earth's atmosphere found balance. It is thick enough to protect, yet thin enough to allow heat to escape. Nitrogen and oxygen mix in proportions that sustain complex organisms. A magnetic field generated by Earth's rotating iron core shields the surface from harmful solar radiation. Without this invisible shield, much of our atmosphere might have been stripped away by the solar wind long ago. Time passed, slowly and steadily. Within the oceans, simple chemical reactions began forming complex molecules. Those molecules organized, replicated, and evolved. Life emerged quietly, perhaps near deep-sea hydrothermal vents where warmth and minerals met cold ocean water. For billions of years, life remained microscopic. Tiny organisms transformed the atmosphere itself, releasing oxygen as a byproduct of photosynthesis. The sky changed. The planet breathed differently. Continents drifted across the surface in a slow geological dance known as plate tectonics. Mountains rose and eroded. Ice ages came and went. Forests expanded, retreated, and expanded again. Through it all, Earth maintained a delicate equilibrium, never perfectly stable, but resilient. If you could watch Earth from space over a single day, you would see weather systems swirling like living brushstrokes. Storms spiral across oceans. Lightning flashes within clouds. Night falls across continents, and cities sparkle with artificial constellations, tiny lights mirroring the stars above. The rotation of the planet creates a rhythm, day turning into night, night into day, a gentle pulse that governs life cycles. From orbit, astronauts often describe a profound sense of unity when viewing Earth. There are no visible lines dividing nations, no markers separating cultures. Only one continuous surface wrapped in atmosphere, floating in silence. This perspective has been called the overview effect, a shift in awareness that comes from seeing our world as a single, interconnected whole. Yet Earth is not isolated. It is part of a complex gravitational relationship with its neighbors. The moon's steady pull creates tides in the oceans, subtle rises and falls that have influenced marine life for millions of years. The gravity of distant planets, especially massive Jupiter, helps shape the stability of the solar system, reducing the number of catastrophic impacts that reach the inner planets. The surface of Earth is dynamic. Volcanoes release pressure from below. Earthquakes remind us that the crust is not fixed but shifting. Rivers carve canyons with patient persistence. Glaciers sculpt valleys over thousands of years. All of these processes continue quietly, shaping landscapes long before any human eye observes them. And then, very recently in cosmic terms, humans appeared. In less than a fraction of a second compared to the age of the solar system, we developed language, science, art, and curiosity. We began asking questions about the sky. We tracked the movements of planets. We built telescopes and eventually spacecraft. We left our atmosphere and looked back. In 1972, during the Apollo 17 mission, astronauts captured an image known as the blue marble, showing Earth fully illuminated against space. That photograph became one of the most reproduced images in history, not because it was technically complex, but because it revealed something emotionally simple: home. Earth's uniqueness lies not only in its oceans or forests, but in its balance. It exists in what scientists call the habitable zone, the region around the sun where temperatures allow liquid water to remain stable. Too close and water would evaporate. Too far and it would freeze. Earth occupies that narrow band with quiet precision. As you imagine our planet now, turning gently beneath drifting clouds, consider how rare such a balance may be. Among the rocky worlds near the sun, only Earth carries vast oceans and breathable air. Only Earth hums with layered ecosystems and countless forms of life. From space, Earth is both ordinary and miraculous. It follows the same gravitational laws as every other planet. It formed from the same dust. And yet, through countless subtle conditions aligning over billions of years, it became a place where awareness itself could arise, where beings could look up at the stars and wonder. Tonight, as you settle into stillness, picture Earth rotating slowly in the darkness, blue and white and peaceful. The sun illuminates one hemisphere while the other rests in night. Clouds drift over oceans. The moon glides silently nearby. And beyond this fragile sphere, the solar system continues outward, growing colder, wider, and more mysterious. Ahead lies a red world shaped by dust storms and ancient valleys, a planet that once may have carried water like Earth does now. As we move outward from the blue serenity of Earth, crossing the quiet path of its orbit, the light begins to soften and cool. The sun appears slightly smaller here, though still warm and constant. Ahead, suspended in the dark like a glowing ember, is a world that has captured human imagination for centuries. It shines with a subtle reddish hue, sometimes bright, sometimes faint, depending on where it travels in its orbit. This is Mars, often called the Red Planet. From a distance, Mars looks calm and smooth, its rusty color shaped by iron oxide dust that coats much of its surface. But as we draw closer, details emerge. Vast plains stretch across its terrain, interrupted by towering volcanoes, deep canyons, and impact craters left by ancient collisions. The planet feels both familiar and distant at the same time, like a quiet echo of Earth's distant past. Mars is smaller than Earth, only about half its diameter, and its gravity is gentler. If you were to walk across its surface, your steps would feel lighter, as though the planet were softly lifting you with each movement. The sky above would not be blue but a muted salmon color during the day, shifting towards soft purples at sunset as fine dust particles scatter sunlight in delicate ways. One of the most striking features of Mars is Olympus Mons, the largest volcano in the entire solar system. It rises nearly 3 times higher than Mount Everest, its slopes stretching across hundreds of kilometers. Imagine standing near its base. The curvature of the planet would hide its peak from view. This enormous shield volcano formed over millions of years, layer upon layer of lava flowing gently outward. Mars lacks the active plate tectonics that reshape Earth's crust, so volcanic hotspots remained fixed in one place, allowing Olympus Mons to grow undisturbed. Not far away lies Valles Marineris, a canyon system so vast it dwarfs Earth's Grand Canyon. It extends for thousands of kilometers, carved not by a single river but likely by a combination of tectonic stretching and ancient water flow. Its walls plunge deep into shadow, revealing layers of rock that preserve the planet's geological history like pages in a book. And water, this is the quiet question that surrounds Mars. Today, its surface is cold and dry. Liquid water cannot remain stable for long under its thin atmosphere, which is composed mostly of carbon dioxide. Temperatures often fall far below freezing. Yet the landscape tells a different story. There are dried riverbeds etched into the ground, delta formations where water once pooled, and minerals that form only in the presence of liquid water. Billions of years ago, Mars may have been warmer and wetter. It may have had lakes, rivers, perhaps even shallow seas reflecting the young sun. A thicker atmosphere could have trapped heat, allowing water to flow across its surface. Over time, however, something changed. Mars's smaller size meant its internal heat dissipated more quickly than Earth's. its magnetic field weakened and eventually faded. Without that protective shield, solar wind gradually stripped away much of its atmosphere, leaving the planet exposed and cold. Yet even now, water has not entirely disappeared. Frozen water ice lies beneath the surface, especially near the poles, where seasonal caps of carbon dioxide frost grow and shrink with the Martian year. Spacecraft observations have revealed subsurface ice deposits and hints of briny flows that may occasionally streak down crater walls during warmer periods. For centuries, humans have looked at Mars with curiosity and wonder. In the late 19th century, telescopic observations led to speculation about canals on its surface, inspiring stories of intelligent life. Though those canals were illusions created by optical limitations, they sparked generations of imagination. Mars became a symbol of mystery and possibility. In recent decades, robotic explorers have carried our curiosity directly to the Martian soil. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have traveled across its surface, sending back images of rocky landscapes under pale skies. They have drilled into ancient sediments, searching for signs that microbial life may once have existed. Each discovery adds another gentle piece to the puzzle of Mars's history. The atmosphere of Mars, though thin, supports weather. Dust storms can sweep across entire continents, sometimes engulfing the planet in a global haze that lasts for weeks. These storms are driven by temperature differences and seasonal changes, lifting fine particles into the air. Despite their scale, they move silently in the vacuum-thin atmosphere, their power felt more than heard. Mars also carries two small moons, Phobos and Deimos, irregularly shaped and likely captured asteroids. Phobos, the larger of the two, orbits very close to the planet and is slowly spiraling inward. In tens of millions of years, it may break apart or collide with the surface, adding yet another chapter to Mars's evolving story. As you imagine standing on Mars tonight, picture the sun setting slowly over a dusty horizon. The light fades gently, casting long shadows across ancient rocks. The temperature drops. Above you, the sky darkens to reveal stars shining clearly in the thin atmosphere. Earth would appear as a small bright point among them, distant yet connected. Mars feels like a memory, a reminder that planets can change dramatically over time. It invites questions about resilience, about transformation, about what conditions allow life to begin and persist. It is neither entirely barren nor fully alive, but something in between, holding clues to both past warmth and present stillness. Beyond Mars lies a region where rocky worlds give way to giants, where gravity grows immense and rings of ice and stone circle colossal planets. The journey outward becomes grander, colder, and more majestic. Ahead waits the largest planet of all, a world of swirling storms and immense presence, shaping the architecture of the solar system itself. As we leave the quiet red plains of Mars behind, the solar system begins to feel wider, grander, and more spacious. The distance between worlds stretches farther now. The sun, though still brilliant, appears smaller in the dark expanse. Ahead, dominating this region like a silent monarch, is a planet so large that all the other planets combined could fit within it. Slowly rotating in bands of cream, gold, and rust, this immense world is Jupiter. From afar, Jupiter looks like a living painting. Broad stripes wrap around its spherical form, alternating light zones and darker belts created by powerful atmospheric currents. These bands are not static. They shift, churn, and evolve over time. Towering clouds rise and fall within them, driven by internal heat escaping from the planet's core. Unlike the rocky worlds we have visited so far, Jupiter does not have a solid surface in the way Earth or Mars does. It is a gas giant, composed mostly of hydrogen and helium, similar to the Sun but without the mass required to ignite nuclear fusion. As we draw closer, one feature immediately captures attention: a vast storm swirling in Jupiter's southern hemisphere. Known as the Great Red Spot, this enormous vortex has been raging for at least 3 centuries, possibly longer. It is so large that Earth itself could fit within its boundaries. The storm rotates slowly, its crimson hues shifting subtly as winds exceeding hundreds of kilometers per hour whip around its center. Yet even this colossal storm is only one element in a constantly shifting atmosphere filled with lightning, towering cloud tops, and deep turbulence hidden beneath the visible layers. Jupiter's scale reshapes your sense of proportion. Its diameter is more than 11 times that of Earth. If Earth were the size of a grape, Jupiter would be closer to a grapefruit resting beside it. But size alone does not define its influence. Jupiter's gravity is immense, and it has played a critical role in shaping the solar system's architecture since its earliest days. During the formation of the planets, Jupiter likely formed quickly, gathering mass from the protoplanetary disk while gas was still abundant. Its rapid growth allowed it to capture a thick envelope of hydrogen and helium. As it settled into orbit, its gravity sculpted the surrounding regions, influencing the distribution of asteroids and comets. Some scientists believe Jupiter may have migrated slightly inward and then outward in the early solar system, altering the paths of smaller bodies and affecting the development of the inner planets. Even today, Jupiter acts as a gravitational guardian. Many comets and asteroids that might otherwise travel toward the inner solar system are redirected or captured by its powerful pull. This protective effect may have reduced the frequency of catastrophic impacts on Earth, subtly supporting the long-term stability required for life to evolve. In this way, Jupiter's presence echoes quietly through the history of our own world. Though it lacks a solid surface, Jupiter does have structure. As you descend into its atmosphere, pressure and temperature increase dramatically. Hydrogen gas gradually transitions into a strange state known as metallic hydrogen, where it behaves like an electrical conductor. This layer, deep within the planet, generates a magnetic field stronger than that of any other planet in the solar system. Jupiter's magnetosphere extends millions of kilometers into space, capturing charged particles and creating intense radiation belts. Orbiting this giant world is a complex family of moons, more than 90 discovered so far. Among them are 4 particularly large companions first observed by Galileo Galilei in 1610. These Galilean moons, Io, Europa, Ganymede, and Callisto, each carry their own unique stories. Io is volcanically active, its surface reshaped constantly by eruptions driven by tidal heating. Europa hides a global ocean beneath its icy crust, raising tantalizing questions about potential life. Ganymede is the largest moon in the solar system, even bigger than Mercury, and possesses its own magnetic field. Callisto, heavily cratered, preserves a record of ancient impacts. Jupiter's gravitational influence on these moons creates tidal forces that flex and heat their interiors. This process generates energy, particularly in Io and Europa, shaping their geologies in remarkable ways. The giant planet's presence is not passive, it actively sculpts the environments of its satellites. If you could float above Jupiter's cloud tops, you would see lightning storms illuminating the darkness beneath swirling layers. You would witness polar cyclones arranged in geometric patterns near the planet's poles, forming a mesmerizing symmetry. The rotation of Jupiter is swift. It completes a full spin in just under 10 hours, making it the fastest spinning planet in the solar system. This rapid rotation contributes to the flattening of its shape and the dramatic banding of its atmosphere. Despite its immensity, Jupiter emits more heat than it receives from the Sun. Residual heat from its formation continues to radiate outward slowly, a reminder that planets carry memories of their birth deep within their cores. It glows faintly in infrared, a quiet warmth in the cold outer reaches. From a distance, Jupiter commands attention, yet there is something calming about its steady presence. It moves along its orbit over nearly 12 Earth years, unhurried and consistent. Its storms rage, but they follow patterns governed by physics and time. It is powerful but not chaotic without purpose. As you imagine Jupiter tonight, picture its vast striped surface turning slowly in the dark, the great red spot drifting across its face like an ancient eye. Its moons circle gracefully, each reflecting faint sunlight. The Sun, smaller here, casts a softer glow, and beyond Jupiter's orbit lies a realm even more distant and serene. Further outward, the temperature drops, and another ringed world awaits, elegant, pale, and encircled by shimmering bands of ice and stone. As we drift outward beyond the immense gravity of Jupiter, the solar system grows quieter, colder, and more spacious. The sun now appears smaller, casting a softer light across this distant region. And ahead, suspended like a carefully placed ornament in the dark, is one of the most breathtaking sights in our cosmic neighborhood. Pale gold, serene, and encircled by luminous bands, this is Saturn. Even from far away, Saturn's rings are unmistakable. They stretch outward in delicate arcs, thin yet vast, composed of countless particles of ice and rock ranging from grains no larger than sand to fragments the size of mountains. Though they appear solid from a distance, the rings are in fact a complex system of orbiting debris, each piece following its own precise gravitational path around the planet. The overall effect is one of elegance, a quiet symmetry that seems almost too perfect to be natural, and yet entirely so. Saturn itself is a gas giant, slightly smaller than Jupiter but still enormous compared to Earth. Like Jupiter, it is composed primarily of hydrogen and helium, with no solid surface in the traditional sense. Its atmosphere forms soft horizontal bands, though more subtle and muted in color than those of its larger neighbor. Creams, pale yellows, and faint browns blend together under the filtered sunlight. One of Saturn's most remarkable qualities is its density. Despite its vast size, it is the least dense planet in the solar system. In theory, if you could find an ocean large enough, Saturn would float. This surprising fact adds to its gentle image, though beneath its calm exterior lie powerful winds and deep internal pressures. Its atmosphere hosts storms and jet streams that circle the planet at tremendous speeds, and near its north pole, a persistent hexagonal storm system rotates in a striking geometric pattern, a natural shape carved by fluid dynamics. The rings of Saturn are not uniform. They are divided into distinct sections separated by dark gaps, most notably the Cassini division. These gaps are shaped by the gravitational influence of Saturn's many moons, which act as shepherds, maintaining the structure of the rings through subtle gravitational interactions. The rings are surprisingly thin compared to their width, in many places only about 10 meters thick, yet they extend hundreds of thousands of kilometers across. If you could stand on one of Saturn's inner moons and look up, the rings would arc across the sky in a shimmering band, reflecting sunlight like frozen rain suspended in orbit. They would cast faint shadows onto the planet below and onto each other, shifting gently as Saturn travels along its nearly 30-year orbit around the Sun. Saturn's family of moons is extensive and diverse, with more than 80 confirmed satellites. Among them is Titan, a world larger than the planet Mercury and shrouded in a thick, nitrogen-rich atmosphere. Titan is unique in the solar system for having stable lakes and rivers on its surface, not of water, but of liquid methane and ethane. Beneath its orange haze, complex organic chemistry unfolds in ways that intrigue scientists searching for clues about the origins of life. Another moon, Enceladus, is small and icy, yet astonishingly active. Jets of water vapor and ice particles erupt from fractures near its south pole, spraying material into space and feeding one of Saturn's rings. Beneath Enceladus's frozen crust lies a subsurface ocean kept warm by tidal heating. This hidden ocean makes Enceladus one of the most promising places in the solar system to search for microbial life. Saturn's gravitational presence shapes its surroundings in subtle but meaningful ways. Its rings may be remnants of a moon torn apart by tidal forces long ago, or perhaps leftover material that never fully formed into a larger body. Whatever their origin, they are not permanent. Over millions of years, the rings slowly lose material, drifting inward toward the planet. They are transient on cosmic timescales, a fleeting beauty in an otherwise ancient system. The planet rotates quickly, completing a full spin in just over 10 hours. This rapid rotation causes it to bulge at the equator, giving it a slightly flattened appearance. Deep within, layers of hydrogen transition under immense pressure, possibly forming metallic hydrogen similar to that within Jupiter, generating a strong magnetic field that stretches far into space. From Earth, Saturn appears as a steady golden light moving slowly among the stars. Through even a modest telescope, its rings become visible, transforming it from a simple point of light into a miniature solar system of its own. For many who first see Saturn through a telescope, it becomes an unforgettable moment, a realization that the universe contains wonders beyond everyday experience. As you imagine Saturn tonight, picture its rings glowing softly under distant sunlight, casting delicate shadows across its cloud tops. Imagine Titan drifting nearby, cloaked in orange mist, and Enceladus quietly releasing plumes into space. The entire system moves together in harmony, bound by gravity and time. Beyond Saturn lies a region where sunlight grows fainter still. The giants continue, but they become more distant, colder, and more mysterious. Their colors shift toward blue, their atmospheres driven by extreme winds far from the sun's warmth. Our journey outward continues, toward a planet tipped dramatically on its side, rotating in a way unlike any other. Beyond the elegant rings of Saturn, the solar system begins to feel profoundly distant. The sun, once a dominant presence in the sky, now appears smaller and softer, casting a pale light across a colder frontier. Here, in the quiet blue twilight of the outer solar system, drifts a world unlike any we have seen so far. Smooth, subtle, and almost dreamlike in color, this is Uranus. From a distance, Uranus looks calm, a nearly featureless sphere tinted a gentle cyan blue. Its color comes from methane gas in its upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue tones back into space. There are no bold stripes like Jupiter's, no dramatic golden haze like Saturn's. At first glance, Uranus appears almost still, like a polished marble turning quietly in the dark. But Uranus holds a remarkable secret. Unlike every other planet we have visited, it does not spin upright. Instead, it is tilted at an extreme angle of about 98 degrees. Imagine a planet lying on its side, rolling along its orbit like a slow-moving wheel. This unusual tilt likely resulted from a massive collision early in its history, when a planetary-sized object struck it and altered its orientation forever. Because of this tilt, Uranus experiences seasons unlike any other planet. For nearly a quarter of its 84 Earth-year orbit, one pole faces directly toward the sun while the other remains in continuous darkness. This means that each pole experiences about 42 years of daylight followed by 42 years of night. The transitions between these extremes are gradual, unfolding slowly over decades. It is a world where time stretches gently, where seasons are measured not in months but in generations. Despite its tranquil appearance, Uranus is far from inactive. Beneath its upper atmosphere lies a mantle composed of water, ammonia, and methane ices. Not solid ice as we know it, but a dense, hot fluid mixture under immense pressure. For this reason, Uranus is classified as an ice giant, distinct from the gas giants Jupiter and Saturn. Deep within, temperatures rise and pressures intensify, though Uranus radiates surprisingly little internal heat compared to Neptune or Jupiter. It remains a mystery why this planet seems to emit less energy than expected. High in its atmosphere, winds can reach speeds of hundreds of kilometers per hour, sweeping across the planet's surface in invisible currents. Though its cloud patterns are subtle, telescopes have occasionally revealed bright storms forming and dissipating, especially as Uranus approaches equinox and sunlight reaches previously shadowed regions. Encircling Uranus is a system of faint, dark rings. They are much less luminous than Saturn's, composed of rocky debris and charcoal-colored particles. Discovered in 1977, these rings were found not through direct imaging but when they briefly blocked starlight as Uranus passed in front of distant stars. Their presence adds another layer of quiet complexity to this distant world. Uranus is accompanied by a family of moons, many of them named after characters from the works of William Shakespeare and Alexander Pope, a poetic tradition unique among planetary systems. Among its largest moons is Titania, a world marked by deep canyons and icy plains. Another, Miranda, presents a particularly strange landscape, with towering cliffs and patchwork terrain suggesting a turbulent geological past. The sideways orientation of Uranus gives its moons unusual orbital dynamics. As the planet rolls around the sun, its ring system and satellites follow, creating a visual spectacle unlike anything else in the solar system. If you could observe Uranus from afar over many years, You would see its poles alternately bask in sunlight and sink into darkness, the entire planet turning as though reclining in space. The discovery of Uranus itself was a quiet revolution in astronomy. In 1781, astronomer William Herschel observed a faint object moving among the stars. At first, he believed it to be a comet, but further observation revealed it to be a new planet, the first discovered with a telescope. Until that moment, humanity had known only the 5 planets visible to the naked eye. Uranus expanded the known boundaries of the solar system, reminding us that there were still worlds waiting beyond the familiar. In many ways, Uranus embodies subtlety. It does not display dramatic storms like Jupiter's Great Red Spot. It does not dazzle with brilliant rings like Saturn. Instead, it invites patience. Its beauty reveals itself slowly, in faint rings, pale storms, and the extraordinary geometry of its tilt. As you imagine Uranus tonight, picture a serene blue sphere rolling gently along its orbit, its rings forming a vertical halo in the faint sunlight. One hemisphere rests in prolonged darkness, stars shining clearly above it, while the other bathes in a distant glow. The cold here is profound, with temperatures dropping to some of the lowest recorded in the solar system. Beyond Uranus lies the outermost of the major planets, a deeper blue world shaped by powerful winds and hidden storms. The sun grows even smaller, and the solar system stretches toward its final planetary boundary. Beyond the tilted calm of Uranus, the solar system stretches farther still into a realm where sunlight fades into a gentle glow. The warmth of the inner worlds feels like a distant memory now. Here, in the outermost reaches of the planetary family, moves a deep blue sphere wrapped in motion and mystery. This is Neptune, the final major planet orbiting our Sun. From afar, Neptune's color is striking, a rich, saturated blue deeper than that of Uranus. Methane in its atmosphere absorbs red light, but additional atmospheric processes enhance its vivid tone, giving it a bold presence despite the faint sunlight it receives. At this distance, the Sun appears as a brilliant star rather than a dominating disk, shining at less than 1/1000th of the brightness seen from Earth. And yet, Neptune is anything but still. Though it lies farther from the Sun than any other planet, Neptune hosts the fastest winds in the entire solar system. Jet streams roar across its atmosphere at speeds exceeding 2,000 kilometers per hour. These winds whip around the planet in massive bands, creating storms that rival or exceed those on Jupiter in intensity. The energy driving these winds does not come primarily from the Sun. Instead, Neptune radiates internal heat, more than twice the energy it receives from sunlight, fueling its dynamic weather from within. In 1989, when NASA's Voyager 2 spacecraft flew past Neptune, it captured images of a massive storm system known as the Great Dark Spot. Similar in size to Earth, this storm resembled Jupiter's Great Red Spot but appeared dark against Neptune's blue clouds. Unlike Jupiter's long-lived storm, Neptune's dark spots seem to form and dissipate over years or decades, shifting and evolving in ways that remain partially mysterious. Bright methane clouds occasionally form high in the atmosphere, drifting like luminous brushstrokes above darker layers. Neptune takes about 165 Earth years to complete one orbit around the Sun. Since its discovery in 1846, it has completed only a single full revolution. Its path was not found by direct observation at first, but by mathematics. Astronomers noticed irregularities in the orbit of Uranus and predicted that another unseen planet must be exerting gravitational influence. Their calculations led to Neptune's discovery, a triumph of science guided by logic and patience. Encircling Neptune are faint rings composed of dark particles and icy debris. They are thinner and less prominent than Saturn's rings, but they exist nonetheless, shaped by the gravitational pull of nearby moons. One of these moons stands out above the rest, Triton. Triton is a remarkable world. It orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. This unusual motion suggests that Triton did not form alongside Neptune but was likely captured long ago, perhaps once a dwarf planet wandering the outer solar system. Triton's surface is icy and pale, marked by geysers that spray nitrogen gas into space. Beneath its frozen crust, There may be a subsurface ocean kept warm by tidal forces, a hidden reservoir beneath layers of frost. If you could stand on Triton and look up, Neptune would dominate the sky, a vast blue presence looming overhead. The distant sun would appear small and brilliant, casting faint light across icy plains. The cold here is extreme, among the most frigid environments in the solar system. And yet, even in this cold, motion persists. Geysers erupt softly. Winds move across Neptune's atmosphere. Orbits continue with unwavering precision. Neptune's magnetic field is tilted and offset from its center, creating complex interactions with the solar wind. Auroras shimmer near its poles, faint but present, shaped by charged particles spiraling along magnetic lines. Even at the edge of light, energy flows and dances. Beyond Neptune lies a vast region once thought empty, a quiet boundary marking the end of the known planets. But as telescopes grew more powerful, astronomers began to detect small icy worlds scattered beyond Neptune's orbit. This distant zone, known as the Kuiper Belt, contains remnants from the early solar system, fragments that never merged into full-sized planets. For a long time, Neptune was considered the final frontier. It represented the outer limit, the farthest known world. But in truth, it is more like a gateway, the last of the great planets before the solar system fades into scattered ice and distant shadows. As you imagine Neptune tonight, picture its deep blue form turning slowly in near darkness. High-speed winds carve patterns into its cloud tops. Triton drifts silently nearby, its icy surface glowing faintly. The sun is small but steady, a distant anchor in the sky. There is a certain serenity here, at the edge of planetary light. The major worlds are behind us now. What remains are ancient remnants, dwarf planets, icy bodies, and long-period comets that wander in from even farther realms. Our journey will continue outward, into the Kuiper Belt, where one small world once held the title of planet and still captures our curiosity. Beyond the deep blue majesty of Neptune lies a colder, quieter region, where sunlight falls faintly and slowly across the surfaces of icy bodies. Here, the solar system begins to feel vast in a way that challenges the imagination. Among these distant worlds drifts a small, intriguing sphere that for decades was considered the ninth planet. This is Pluto, a distant sentinel at the edge of our solar neighborhood. Pluto is small, even compared to Earth's moon. Its diameter is only about 2/3 that of the moon, yet it carries a presence that has fascinated astronomers and the public alike. Its surface is a mosaic of plains, mountains, and craters, coated with nitrogen, methane, and carbon monoxide ices. From a distance, Pluto appears pale and distant, a tiny point of light drifting in the darkness. But up close, its landscapes are dramatic, surprisingly varied, and alive with texture. The New Horizons mission in 2015 revealed Pluto's astonishing complexity. Vast plains like Sputnik Planitia stretch across its surface, smooth and reflective, hinting at slow geological processes that renew the ice over time. Towering mountains of water ice rise sharply from the plains, jagged and frozen, remnants of a dynamic past. Craters mark impacts from the early solar system, but the ongoing reshaping of the surface suggests Pluto has retained internal energy, quietly active beneath its frozen exterior. Pluto's atmosphere is thin and ephemeral, composed primarily of nitrogen with traces of methane and carbon monoxide. When it is closer to the Sun in its elliptical orbit, ices sublimate, creating a tenuous haze that rises and spreads, forming delicate layers above the surface. As Pluto moves farther from the Sun, these gases freeze again, falling back to coat the terrain. Its atmosphere appears almost like a slow breath, inhaling and exhaling over decades as it travels along its 248-year orbit. One of Pluto's most remarkable features is its heart-shaped region, informally called Tomball Regio. This vast plain, bright and smooth, has become a symbol of Pluto itself, a frozen heart at the edge of the solar system, quietly reflecting sunlight and inviting curiosity. Adjacent to it lie mountains, valleys, and streaks of darker material, all telling a story of a world that is small yet remarkably intricate. Pluto also has a family of moons, the largest of which is Charon. Comparable in size to half of Pluto itself, Charon is gravitationally locked with Pluto, meaning both bodies always show the same face to each other as they orbit their shared center of mass. This dance creates a serene cosmic rhythm, a quiet companionship in the outer darkness. Other smaller moons, Styx, Nix, Kerberos, and Hydra, circle at greater distances, adding to the sense of a small, yet complete system. Pluto's orbit is unique. It is highly elliptical and tilted relative to the plane of the solar system. At times, Pluto even comes closer to the Sun than Neptune, though their paths never intersect due to a precise gravitational resonance that maintains stability over millions of years. This distant wanderer moves slowly, almost meditatively, through the Kuiper Belt, carrying within it the history of the outer solar system. Though no longer classified as a full planet, Pluto's significance remains immense. It embodies the frontier of exploration, the edge of what we know, and the promise of what lies beyond. Its discovery in 1930 marked the beginning of humanity's awareness of the outer solar system. Its demotion in 2006 to dwarf planet status sparked debate but did nothing to diminish the fascination it inspires. As you imagine Pluto tonight, picture it drifting quietly in the dark, a pale sphere reflecting a weak, distant Sunday. Charon orbits nearby, locked in their eternal gravitational embrace. The other moons circle silently, tiny companions in an expansive icy realm. Here, at the edge of sunlight's reach, the solar system opens into a vast expanse of frozen worlds. The Kuiper Belt stretches farther still, populated by countless icy remnants of the solar nebula, objects that never coalesced into planets, but that hold the memory of the system's birth. Beyond Pluto, some of these bodies wander alone. Others cluster in small families, each orbiting the Sun slowly, patiently, quietly. They are the sentinels of the distant solar system, preserving secrets from billions of years ago. Next, we will glide through this mysterious Kuiper Belt, exploring these icy remnants and small worlds that drift in the quiet outer darkness. Beyond Pluto's quiet orbit, where sunlight becomes only a faint suggestion of warmth, lies a vast ring of icy debris that stretches across billions of kilometers. This region is known as the Kuiper Belt, a distant frontier filled with ancient remnants of the solar system's birth. Here, countless small worlds drift slowly through darkness, preserved like frozen memories from the early days of planetary formation. This region is home to many objects similar to Pluto, all sharing a common origin in the primordial solar disk. The Kuiper Belt is not empty space. Instead, it is filled with millions of icy bodies, rock mixed with frozen water, methane, and ammonia. These objects rarely collide, because the distances between them are enormous. Instead, they orbit in quiet solitude, moving so slowly that their journeys around the Sun can take hundreds of years. Time here feels different, stretched and patient, like a deep sleep that lasts for centuries. Many Kuiper Belt objects are irregular in shape. Unlike planets, which have enough gravity to pull themselves into spheres, these smaller bodies remain lumpy and uneven, shaped by ancient impacts and slow gravitational settling. Some are bright and reflective, while others are dark, coated in organic compounds created by cosmic radiation over billions of years. These dark surfaces give them a mysterious, almost ancient appearance, like charcoal stones floating in space. The Kuiper Belt is believed to be the source of many short-period comets that occasionally visit the inner solar system. When gravitational disturbances push these icy bodies inward, they begin to warm as they approach the Sun. Their frozen materials vaporize, forming glowing tails that stretch behind them like soft streams of light. These comets are like travelers waking from long hibernation, briefly visiting the warmer regions before returning to the cold outer darkness. Among the most fascinating Kuiper Belt inhabitants is Haumea, a world that rotates so quickly that it is stretched into an oval shape. Haumea spins once every 4 hours, one of the fastest rotations of any large object in the solar system. This rapid spinning likely resulted from a massive collision long ago, scattering fragments that later became its moons. Haumea's surface is covered in crystalline water ice, giving it an unusually bright and reflective appearance. Another distant resident is Makemake, a reddish dwarf planet discovered in 2005. Makemake lacks a significant atmosphere, leaving its surface exposed to cosmic radiation that slowly alters its chemistry over time. Its reddish tint comes from complex organic molecules known as tholins, formed when sunlight and radiation interact with frozen methane compounds. Further outward, still within the Kuiper Belt, lies Eris, a world slightly more massive than Pluto itself. Eris played an important role in the redefinition of planetary classification in 2006, when astronomers began realizing that Pluto was only one member of a much larger population of similar objects. Eris follows an extremely elongated orbit, taking nearly 560 Earth years to complete one journey around the Sun. The Kuiper Belt is sometimes compared to a cosmic fossil record. Just as fossils preserve life from ancient Earth, Kuiper Belt objects preserve materials from the solar system's earliest days. Studying them allows scientists to understand the composition of the protoplanetary disk that gave birth to the planets. These objects have changed very little over billions of years, making them valuable scientific time capsules. Beyond the Kuiper Belt lies an even more mysterious region, one that is not a flat ring but a vast spherical shell surrounding the entire solar system. This region is called the Oort cloud, a theoretical boundary filled with icy objects that drift in extremely long orbits. Some of these objects may take tens of thousands of years to complete a single trip around the Sun. The Kuiper Belt marks a transition between the familiar planetary family and the truly distant solar wilderness. Here, the Sun is no longer a source of warmth but only a bright star among many others. Day and night lose meaning because rotation and illumination become slow and subtle processes measured across long geological time. If you could stand on one of these distant icy worlds, the sky would appear black even during the day. The Sun would shine as a tiny, brilliant point of light. Stars would be visible at all times, not hidden by atmospheric scattering. The silence would feel absolute. No wind, no sound, only the slow passage of time and the distant glow of the inner solar system. The Kuiper Belt also represents a bridge between planetary science and interstellar space. Objects drifting here are influenced not only by the Sun but also by passing stars and galactic tides, subtle gravitational forces from the wider Milky Way galaxy that can nudge comets toward the inner solar system. As you imagine this region tonight, picture countless icy worlds drifting slowly through eternal twilight. Some are smooth and bright, others are dark and ancient. All of them carry the history of planetary creation within their frozen surfaces. Beyond the Kuiper Belt, space becomes even more mysterious. The Sun's influence weakens, gravity's grip stretches thinner, and there begins a vast region where long-period comets are born, the distant, spherical boundary of our solar system. Our journey now moves toward that ultimate frontier of the Sun's influence, where darkness deepens and distances become almost incomprehensible. Beyond the scattered icy worlds of the Kuiper Belt, the solar system does not simply end. Instead, it slowly fades into a vast, mysterious boundary where the Sun's gravity still holds influence, but only barely. This boundary is not a flat disk like the planetary orbits, but a massive spherical shell surrounding the entire solar system. Scientists call this distant region the Oort cloud, a theoretical realm filled with trillions of icy objects slowly drifting in enormous orbits around the Sun. Within this distant darkness, even objects like Eris would seem relatively close compared to the farthest reaches of this region. The Oort cloud is so vast that its inner boundary may begin thousands of times farther from the Sun than Earth's orbit. Its outer boundary could stretch halfway toward the nearest stars. If the Kuiper Belt is the outer neighborhood of the solar system, then the Oort cloud is the distant countryside, quiet, remote, and almost entirely untouched by sunlight. Objects in the Oort cloud are believed to be remnants of the early solar system, similar to those in the Kuiper Belt, but scattered outward by gravitational interactions with the giant planets during the solar system's formation. As Jupiter and Saturn grew massive, their gravity likely flung countless icy bodies outward, pushing them into distant orbits where they have remained frozen ever since. Unlike planets, Oort cloud objects do not follow orderly paths within a single plane. Instead, their orbits are random and spherical, surrounding the sun like a giant invisible bubble. Some of these objects take tens of thousands, or even millions of years to complete one orbit. To them, time moves extremely slowly. The concept of a year would be almost meaningless. Occasionally, something disturbs these distant objects. Passing stars, gravitational tides from the Milky Way galaxy, or even interactions with interstellar clouds can nudge them from their long sleep. When this happens, they may begin a long journey inward toward the sun, becoming long-period comets. These comets can spend thousands of years traveling toward the inner solar system, only to briefly visit before returning to the deep freeze of the outer reaches. These comets are some of the most beautiful visitors in our sky. As they approach the sun, their ices vaporize, creating glowing comas and long, luminous tails that always point away from the sun due to solar wind and radiation pressure. Ancient civilizations often viewed comets with awe and fear, believing them to be omens of change. Today, we understand them as natural travelers carrying ancient materials from the solar system's birth. The Oort cloud is not something we can directly observe with telescopes because its objects are extremely small and distant. Instead, its existence is inferred from the trajectories of long-period comets entering the inner solar system. These observations suggest a massive reservoir of icy bodies surrounding our system, though its exact size and structure remain uncertain. In this remote region, the sun is nothing more than a very bright star among many others. If you were standing on an Oort cloud object, you might not even notice which star was our sun unless you carefully tracked its movement across the sky. The cold here is absolute, close to the temperature of deep space itself, just a few degrees above absolute zero. The Oort cloud also represents the boundary between our solar system and interstellar space. Beyond it, the sun's gravitational influence weakens until it can no longer hold onto objects. At that point, interstellar space begins, a vast expanse between stars filled with thin gas, dust, and cosmic radiation. Our solar system floats within this wider galactic environment, moving slowly around the center of the Milky Way along with billions of other star systems. The concept of the Oort cloud was first proposed by Dutch astronomer Jan Oort, who studied the distribution of long-period comets and realized they must originate from a distant spherical reservoir. Though no spacecraft has ever reached this region, mathematical models and comet observations strongly support its existence. If you could travel to the Oort cloud, the journey would take generations using current technology. The distances are so vast that space itself would feel stretched and empty. Stars would gradually become brighter and then fade again as you drifted between them. The familiar solar system would shrink behind you until it became just another distant star system in the night. The Oort cloud represents both an ending and a beginning. It marks the limit of our sun's direct influence, yet it also serves as a source of new comets that occasionally bring fresh material into the inner solar system. In this way, it acts like a slow cosmic conveyor belt, connecting the deep past of the solar system with its present. As you imagine this region tonight, picture endless darkness filled with silent icy objects drifting in enormous orbits. Some have not seen sunlight in millions of years. Others are just beginning their long journey inward. Everything here moves slowly, patiently, almost meditatively. And beyond the Oort cloud lies something even more profound, the true beginning of interstellar space, where the influence of our sun fades completely and the stars themselves become our new neighbors. Our journey now moves beyond the solar system itself, toward the great ocean between the stars. Shooting star. Beyond the outer bubble of the Oort cloud, something extraordinary begins. The presence of our sun slowly weakens until it can no longer hold dominion over wandering dust and icy fragments. Gravity becomes faint. Light spreads thin. Space becomes truly vast in a way that is difficult for the human mind to fully comprehend. This is interstellar space, the ocean between stars, the region where our solar system floats like a tiny island within the greater galaxy. In this silent territory, even the idea of a solar system feels distant. The sun is no longer a dominant light source, but simply another star among billions. If you could drift here, you would notice how empty space truly is. Even though we imagine space as crowded with stars, the distances between them are unimaginably large. Most of space is not filled with brilliant objects but with thin hydrogen gas, microscopic dust particles, and faint cosmic radiation traveling endlessly through darkness. One of the first human-made objects to reach this frontier was the spacecraft Voyager 1. Launched in 1977, it traveled past the planets and continued outward, carrying with it a small golden record containing sounds, music, and images of Earth. This record was meant as a message, a quiet greeting to any intelligence that might one day encounter it. Voyager 1 officially entered interstellar space in 2012, crossing a boundary called the heliopause, where the solar wind no longer flows outward with strength. The heliopause is like a cosmic shoreline. On one side lies the solar wind, streams of charged particles flowing outward from the sun. On the other side lies the interstellar medium, a much colder and thinner environment influenced by the broader galaxy. When Voyager 1 crossed this boundary, scientists observed changes in particle density and magnetic fields, confirming that humanity had reached the true edge of our sun's influence. In interstellar space, temperatures are not warm or cold in the way we experience on Earth. Instead, temperature is defined by particle motion. Because particles are so sparse here, heat behaves differently. A human body would not freeze instantly, but the lack of pressure and oxygen would make survival impossible. Silence would be absolute, because sound requires a medium to travel. No wind would blow. No atmospheric movement would exist. Only radiation and darkness would surround you. Yet even here, motion continues. Our solar system itself is moving through space as it orbits the center of the galaxy. This journey takes about 225 to 250 million years to complete, a galactic year. Dinosaurs walked on Earth during the last time our solar system was in a similar position along its galactic orbit. The region of interstellar space is not truly empty. It contains diffuse clouds of gas and dust known as interstellar nebulae. These clouds are the birthplaces of new stars. Over millions of years, gravity can pull this material together, starting the cycle of star formation again. In this way, the death of one star can help create new ones, continuing the cosmic cycle of birth, life, and transformation. Far beyond our solar system, other stars shine with their own planetary families. Some of these stars may host worlds similar to Earth. Astronomers continue searching for exoplanets within the so-called habitable zones of distant stars, hoping to find environments where liquid water could exist. The discovery of such worlds suggests that our solar system may be only one example among countless others scattered across the galaxy. If you could stand in interstellar space and look back toward the sun, it would appear as just another bright star among thousands. Earth would be completely invisible without powerful telescopes. All human history would be compressed into a tiny, unseen world orbiting a distant star. There is something deeply emotional about this perspective. It reminds us how small our world is compared to cosmic scales, yet how remarkable it is that consciousness has emerged here. Every story, every memory, every civilization exists on that tiny blue world we saw earlier in our journey. Interstellar space is not just emptiness. It is transition. It is the bridge between star systems, between past and future, between creation and continuation. The atoms that make up your body may once have been formed inside stars that exploded long before Earth existed. In a sense, we are made of interstellar history. As you imagine this region tonight, picture endless darkness filled with faint starlight scattered across unimaginable distances. Our solar system drifts slowly through this cosmic ocean, carrying with it life, memory, and curiosity. And somewhere far ahead, beyond interstellar space, lie other star systems waiting to be explored, new suns, new planets, and new stories still unfolding in the endless night. Our journey continues outward, toward the greater galactic environment where stars themselves gather in vast communities. Shooting star. As we move even farther from our home star, the scale of existence expands again. Individual stars are no longer the focus. Instead, we begin to see how stars gather together into enormous cosmic cities called galaxies. Our home is part of one such city, a majestic spiral structure known as the Milky Way. This is Milky Way, a vast rotating collection of stars, gas clouds, dust, and dark matter, all bound together by gravity. From a distant viewpoint, the Milky Way would appear as a grand spiral disk slowly rotating in space. Bright arms of stars curve outward from a glowing central bulge. These spiral arms are regions of intense star formation, where dense clouds of gas collapse under gravity to create new stars and planetary systems. Our own solar system lies within one of these spiral arms, far from the crowded galactic center, in a relatively quiet region that may have helped life develop safely over billions of years. The Milky Way contains hundreds of billions of stars. Each of those stars may have its own planets, moons, and asteroid belts. Some may host worlds similar to Earth. Others may host strange, exotic planets made of gas, ice, or even diamond-like materials under extreme pressure. The galaxy is not static. It is alive with motion. Stars orbit the galactic center just as planets orbit stars. At the heart of the Milky Way lies a mysterious and powerful presence, a supermassive black hole known as Sagittarius A star. This object contains the mass of millions of suns compressed into a region smaller than our solar system. Around it, stars move at incredible speeds, sometimes completing orbits in just a few years due to the extreme gravitational forces present there. If you traveled toward the galactic center, the environment would become increasingly chaotic. Star density would increase dramatically. The night sky on any planet there would be filled with brilliant clusters of stars instead of the relatively sparse sky we see from Earth. Radiation levels would be much higher, and stellar collisions would be more likely in those crowded regions. Our Sun orbits the galactic center once every 225 to 250 million years. This journey is called a galactic year. During one galactic year, Earth experiences the rise and fall of entire species, continents shift, ice ages come and go, and civilizations appear and disappear. Humanity has existed for only a tiny fraction of one galactic orbit. The Milky Way is not alone in the universe. It is part of a larger group of galaxies called the Local Group. The closest large neighboring galaxy is Andromeda Galaxy. It is slowly moving toward us at about 110 kilometers per second. In about 4 to 5 billion years, Andromeda and the Milky Way are expected to collide and merge, forming a new, larger galaxy. Despite the dramatic sound of the word collision, the vast distances between stars mean that actual star collisions will be rare. Instead, galaxies will pass through and blend together over millions of years, reshaping their spiral structures. Galaxies are held together not only by visible matter but also by something mysterious called dark matter. Dark matter does not emit or reflect light, so it cannot be seen directly. Scientists detect it through its gravitational effects on stars and gas clouds. Without dark matter, galaxies might not have enough mass to hold themselves together as they rotate. Though we cannot see it, dark matter is believed to make up most of the mass of the universe. If you could float far above the Milky Way, you would witness a slowly rotating spiral disk glowing softly against the darkness of space. Stars would sparkle like dust particles in sunlight, but on a cosmic scale. Nebulae would glow faintly in colors invisible to the human eye without special instruments. The galaxy would feel both immense and peaceful, like a cosmic ocean slowly turning. As you imagine this tonight, think of the Milky Way as a vast river of stars flowing through space and time. Our solar system is just one small boat traveling along that river. Life on Earth is one brief story written on one small world orbiting one ordinary star. And beyond galaxies like our own lies the largest scale of cosmic structure, the enormous web of galaxy clusters, dark voids, and cosmic filaments that stretch across the universe itself. Our journey now moves toward those grand structures, where galaxies gather like islands in an even larger cosmic sea. Beyond individual galaxies, the universe grows even larger in structure and complexity. Galaxies do not drift alone in isolation. Instead, they gather in massive groups bound together by gravity, forming what scientists call galaxy clusters. These clusters are some of the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies moving slowly around a shared center of mass. Our own galaxy is part of the Local Group, a modest collection of galaxies that includes our spiral home and its neighbors. Within these groups, galaxies interact gravitationally over billions of years. Sometimes they gently pass by each other, their shapes slowly distorted by tidal forces. Other times they merge, forming new galaxies that inherit the stars of their predecessors. Galaxy clusters themselves are often connected by something even larger and more mysterious: the cosmic web. This structure is an enormous network of galaxy filaments separated by vast empty voids. In this web, galaxies are like glowing cities connected by invisible highways of gravity. These filaments are composed mostly of dark matter and thin gases that slowly pull galaxies toward each other over unimaginable timescales. One of the most famous galaxy clusters is the Virgo cluster. It contains thousands of galaxies and acts as a gravitational anchor for nearby galaxy groups. Astronomers believe our local group is slowly drifting toward this massive structure due to gravitational attraction across tens of millions of light years. Between these clusters lie enormous voids, regions of space that are almost completely empty of matter. These voids can span hundreds of millions of light years. If you were to travel through one, you would see almost no galaxies at all, only faint background radiation from the early universe. These cosmic voids make the universe appear like a dark sponge, with matter concentrated along thin edges and vast emptiness in between. The cosmic web formed shortly after the universe itself was born. In the earliest moments after the Big Bang, tiny fluctuations in density allowed matter to clump together under gravity. Over billions of years, these small differences grew larger, eventually forming stars, galaxies, and clusters. In this way, the universe slowly organized itself from near-uniform chaos into structured beauty. Dark matter plays a crucial role in shaping these structures. Although it cannot be seen directly, its gravitational influence acts like an invisible scaffolding holding galaxies and clusters together. Scientists believe dark matter forms massive halos around galaxies, helping them maintain their shapes as they rotate through space. If you could stand outside a galaxy cluster and look upon it from afar, you would see hundreds of galaxies glowing like scattered lanterns across a dark cosmic sky. Some galaxies would appear redder because their light is stretched by the expansion of the universe, a phenomenon called redshift. This stretching of light reveals that the universe itself is expanding, pushing galaxies farther apart over time. This discovery led to one of the most important scientific revelations of the modern age: that the universe is not static but dynamic and evolving. The space between galaxies is growing, carrying galaxies away from each other like dots painted on the surface of an expanding balloon. Yet gravity continues to fight against this expansion on smaller scales. Inside galaxy clusters, gravity is strong enough to hold galaxies together despite the universe's overall expansion. This balance between expansion and attraction shapes the long-term destiny of cosmic structures. The cosmic web is not only a structure of space but also of time. Looking deeper into space means looking further back in time, because light takes time to travel. When astronomers observe distant galaxies, they see them not as they are today but as they were millions or even billions of years ago. In this way, the night sky becomes a living history book of the universe. As you imagine this tonight, picture vast cosmic highways of gravity connecting glowing islands of stars. Picture enormous voids of darkness where almost nothing exists. The universe is not chaotic. It is structured, layered, and quietly evolving. And beyond galaxy clusters lies something even greater, the largest scale structure of all, where the universe itself begins to reveal its origin, its age, and its ultimate fate. If we travel even farther back in time instead of space, we reach the origin of all the cosmic structures we have explored. Before galaxies, before stars, before planets, before even atoms could exist, the universe was compressed into an unimaginable state of density and energy. Then, about 13.8 billion years ago, something extraordinary happened. The universe began to expand from a single, incredibly hot point. This moment is known as the Big Bang. The Big Bang was not an explosion in space. Instead, it was an expansion of space itself. At the earliest moments, the universe was extremely small, hotter than anything that exists today. Temperatures were so high that particles could not yet form stable atoms. Instead, energy existed as a dense sea of radiation and subatomic particles moving at nearly the speed of light. In the first fractions of a second after the Big Bang, fundamental forces of nature began to separate. Gravity, electromagnetism, and nuclear forces gradually took on the properties that govern physics today. As the universe expanded and cooled, particles began to form. Quarks combined into protons and neutrons. These particles later formed the first simple atomic nuclei. Several minutes after the Big Bang, the universe had cooled enough for hydrogen and helium nuclei to form. This period is called primordial nucleosynthesis. These light elements became the building blocks for all future stars and galaxies. For hundreds of millions of years afterward, the universe remained dark, filled only with gas and radiation. This period is often called the cosmic dark age. Eventually, gravity pulled gas clouds together, forming the first stars. These early stars were massive and short-lived, burning through their fuel quickly and ending their lives in powerful supernova explosions. These explosions scattered heavier elements like carbon, oxygen, and iron into space, the elements that would later form planets and life itself. Observations of the universe today strongly support the Big Bang theory. One key piece of evidence is the cosmic microwave background radiation, a faint glow that fills the entire universe. This radiation is the leftover heat from the early universe, stretched into microwave wavelengths as space expanded. It is like a faint echo of the universe's birth still whispering through space. Another piece of evidence is the observed expansion of the universe. Distant galaxies are moving away from us, and the farther away they are, the faster they move. This was first discovered by astronomer Edwin Hubble, who observed that galaxies showed a relationship between distance and redshift. The early universe was incredibly uniform, but tiny fluctuations in density allowed matter to clump together over time. These tiny differences eventually grew into the cosmic structures we see today: stars, galaxies, and clusters spread across the cosmic web. Dark energy is another mysterious force influencing the universe's fate. While gravity tries to pull matter together, dark energy appears to push the universe apart at an accelerating rate. Scientists do not yet fully understand dark energy, but observations suggest it makes up most of the universe's total energy content. If you could witness the Big Bang from outside, you would not see an explosion in space, but rather the rapid expansion of space itself. Galaxies would not be flying away from a central point. Instead, every point in the universe would be expanding away from every other point simultaneously. The Big Bang represents not just the beginning of physical matter, but the beginning of time and space as we understand them. Before it, the concept of before may not have even existed. As you imagine this tonight, picture a universe born from pure energy, expanding silently into darkness, cooling slowly, allowing matter to form, and eventually creating stars, planets, oceans, and life. Everything we know, from the smallest atom to the largest galaxy, traces its history back to this moment. And yet, even the Big Bang may not be the ultimate beginning. Some scientists believe there may have been events before it, or that our universe may be one among many. Beyond the beginning of our universe lies one of the most speculative and fascinating ideas in modern cosmology: the possibility that our universe is not alone. Instead, it may be one of many universes existing simultaneously in something called the multiverse. In this concept, reality itself may be far larger and more complex than we can currently observe or measure. The idea of a multiverse arises from several areas of theoretical physics and cosmology. One possibility comes from inflation theory, which suggests that shortly after the Big Bang, the universe expanded extremely rapidly. During this inflationary period, different regions of space may have stopped inflating at different times, creating separate bubble universes with their own physical laws. Each bubble could have its own version of physics, constants of nature, and even different possibilities for matter and energy. In this framework, our universe would be just one bubble among many floating in a vast cosmic inflation field. Some universes might be similar to ours, with stars and planets. Others might be completely different, with exotic forms of matter or physics that do not allow stars or galaxies to form at all. Another interpretation of the multiverse comes from quantum mechanics. In the quantum world, particles can exist in multiple states at once until they are observed. Some interpretations of quantum theory suggest that every possible outcome of every event may occur in a separate branch of reality. This idea is often called the many worlds interpretation. In this view, every decision you make could theoretically create alternate versions of reality where different choices were made. Imagine, for example, countless versions of Earth existing in parallel. In one universe, humanity may have evolved slightly differently. In another, dinosaurs may never have gone extinct. In yet another, intelligent life may have developed in completely different forms. These universes would not be directly observable to us because they would be separated by fundamental physical barriers. While the multiverse is mathematically possible in some theories, there is currently no direct experimental evidence proving its existence. Scientists continue to search for indirect clues, such as unusual patterns in cosmic background radiation that might suggest collisions between bubble universes. So far, evidence remains inconclusive, leaving the multiverse as one of science's greatest mysteries. Even without proof, the idea of multiple universes has philosophical implications. It challenges our understanding of uniqueness and existence. If countless universes exist, then the probability of any single event happening becomes part of a much larger cosmic probability landscape. In this vast conceptual space, our universe may be just one possible expression of physical laws. Constants like the speed of light, gravitational strength, and electromagnetic forces may take different values elsewhere. If those values were different in our universe, stars might not form, planets might not exist, and life might never arise. This idea connects deeply to the anthropic principle, which suggests that we observe the universe in its current state because only certain physical conditions allow observers like us to exist. In other words, we live in a universe capable of supporting life because otherwise, we would not be here to ask these questions. The multiverse also ties into cosmic destiny. Some theories suggest that our universe may continue expanding forever, eventually becoming cold and dark as stars burn out, a fate sometimes called the heat death of the universe. Other theories suggest that expansion could reverse in a big crunch, collapsing everything back into a dense state. Still others propose cyclic universes, where expansion and collapse repeat endlessly. As you imagine the multiverse tonight, picture reality like an endless ocean of bubbles, each containing its own stars, galaxies, and laws of physics. Some bubbles glow brightly with life. Others remain dark and empty. All of them drift silently through a deeper, hidden structure of existence. And beyond the multiverse, some thinkers ask an even deeper question: what is the true nature of consciousness, reality, and existence itself? Are we simply observers inside the universe, or does observation itself help shape reality? As we move beyond the physical structure of the universe, another mystery appears, not of stars or galaxies, but of something far closer and yet more complex. That mystery is consciousness. While the universe is filled with matter and energy following physical laws, consciousness represents the ability to experience, to think, and to be aware of existence itself. It is perhaps one of the greatest unanswered questions in science and philosophy. Consciousness allows you to read these words, to imagine distant galaxies, and to feel emotions as you journey mentally through the cosmos. Yet scientists still do not fully understand how consciousness arises from physical matter. The human brain contains billions of neurons, each connected through trillions of neural pathways. These neurons communicate using electrical signals and chemical messengers, creating patterns of activity that give rise to thoughts and awareness. Some scientists believe consciousness emerges from complex information processing. In this view, awareness is not a single thing located in one specific part of the brain, but rather a collective phenomenon arising from the interaction of many neural systems. Like waves forming on the surface of an ocean, consciousness may emerge from underlying physical processes without existing as a separate substance. Others propose more mysterious possibilities. Some theories suggest that consciousness might be a fundamental property of the universe itself, similar to space, time, or energy. In this view, consciousness would not be created by the brain but instead filtered through it, like light passing through a prism. This idea remains highly speculative but continues to inspire philosophical and scientific discussion. The relationship between consciousness and reality also raises questions about perception. The world you experience is not a direct representation of external reality but rather a constructed model created by your brain. Your senses detect signals from the environment, which your brain interprets into colors, sounds, and sensations. For example, color is not a property of light itself, but rather how your brain interprets different wavelengths of electromagnetic radiation. This means that every person experiences the universe slightly differently. Two people can observe the same event but interpret it in different ways based on memory, emotion, and perspective. In this sense, reality may be partially shaped by observation and interpretation. This idea connects to concepts in quantum physics, where observation appears to influence the behavior of particles at microscopic scales. While this does not mean consciousness directly controls reality, it suggests that observation plays an important role in how physical systems behave. Consciousness also connects deeply to the concept of identity and time. Humans experience time as a continuous flow from past to future, yet physics suggests time may be more flexible than our perception implies. Some theories even suggest that time may exist as another dimension rather than a flowing stream. From this perspective, past, present, and future may all exist simultaneously, even if we experience them sequentially. The study of consciousness also touches on artificial intelligence. Scientists are working to understand whether machines could ever develop true awareness or whether consciousness requires biological systems. If machines ever achieve consciousness, it could redefine what it means to be alive and aware. On a cosmic scale, consciousness is extremely rare. Out of billions of planets and trillions of stars, we only know of one world where conscious life has definitively emerged: Earth. This makes consciousness one of the most precious and mysterious phenomena in the universe. As you reflect on this tonight, imagine consciousness as a quiet light inside a vast dark universe. Each thinking mind is like a small glowing star of awareness, experiencing reality from its own perspective. Together, all conscious beings create a network of perception that allows the universe to be aware of itself through observation. And beyond consciousness lies one final question. Not about space, not about time, but about the ultimate meaning of existence and the future of intelligent life in the cosmos. As we look forward instead of backward, we reach one of the most profound questions in science. What will happen to the universe in the far future? The universe is not static. It is evolving, expanding, and slowly transforming over billions and trillions of years. The fate of stars, planets, galaxies, and even matter itself depends on cosmic forces still at work today. Right now, the universe is expanding at an accelerating rate, driven by a mysterious phenomenon called dark energy. This expansion is pushing galaxies farther apart from one another. In the distant future, this means that galaxies outside our local region will eventually move so far away that their light will no longer reach us. Future civilizations, if they exist, may look up at the night sky and see only their own galaxy surrounded by darkness. Stars are also slowly dying. Stars like our sun will continue burning hydrogen fuel for billions of years, but eventually they will begin to change. Our sun will expand into a red giant star, possibly engulfing the inner planets, including Earth. Long before that happens, Earth will become too hot to support life as we know it. Oceans may evaporate, and the atmosphere may gradually be lost to space. After the sun exhausts its fuel, it will shed its outer layers and become a white dwarf, a dense, slowly cooling stellar remnant. This is the eventual fate of most medium-sized stars. White dwarfs can remain hot for trillions of years, slowly fading as they radiate away their stored heat. Massive stars have a more dramatic fate. They end their lives in powerful supernova explosions, scattering heavy elements into space. These explosions are essential for cosmic evolution because they create elements heavier than iron, elements necessary for planets, technology, and life. Without supernovae, the universe would remain chemically simple. In the extremely distant future, galaxies may begin to lose their structure. Stars will drift apart, stellar nurseries will cease forming new stars, and the universe will become darker. This stage is sometimes called the degenerate era, when only stellar remnants remain, white dwarfs, neutron stars, and black holes slowly orbiting in darkness. Even black holes will not last forever. According to theoretical physics, black holes may slowly evaporate through a process called Hawking radiation. Over unimaginable timescales, even these cosmic giants may disappear, leaving behind a universe filled with low-energy radiation and scattered particles. This final stage of cosmic evolution is sometimes called the heat death of the universe. In this scenario, entropy, the measure of disorder, reaches maximum levels. Energy differences disappear. No useful work can be performed. The universe becomes a cold, dark, and nearly static place where time continues but change becomes extremely rare. However, not all theories agree on this fate. Some scientists propose alternative endings. The universe could collapse again in a big crunch if gravity eventually overcomes expansion. Others suggest cyclic models, where universes expand, collapse, and are reborn repeatedly. Some even suggest new physics could emerge in the far future that we cannot yet predict. From a human perspective, these timescales are almost impossible to imagine. Trillions of years pass in cosmic evolution, far beyond the lifespan of any civilization we can currently conceive. And yet, these long futures remind us of something profound, that existence itself is part of an enormous, ongoing process. As you imagine the far future tonight, picture stars slowly fading from the sky. Picture galaxies drifting apart into darkness. Picture the universe becoming quieter, more still, but still existing, still expanding, still changing in ways we may not fully understand. And yet, even in this distant future, the story of the universe is not truly finished. Because every ending in cosmic history has also been a beginning for something new. At the end of this long cosmic journey, we return not to a location, but to a question. Not where we are in the universe, but why we are here to witness it. From the birth of stars to the dance of galaxies, from the cold edges of interstellar space to the mysterious origins of consciousness, the universe has revealed itself as both scientifically understandable and emotionally profound. Humanity exists on a small blue planet orbiting a stable star in a quiet region of the Milky Way galaxy. In cosmic terms, this is a fortunate location. We are not too close to the violent radiation of the galactic center, nor too far from the raw materials needed to form planets and life. This balance allowed complex chemistry to emerge and eventually evolve into biological life. Over billions of years, natural selection shaped organisms capable of curiosity, imagination, and technology. The ability to look at the night sky and ask questions may be one of humanity's greatest achievements. Early humans saw patterns in the stars and created myths to explain them. Later civilizations developed astronomy, mathematics, and physics. Today, we send spacecraft beyond our solar system, carrying messages about our existence into interstellar space. Humanity is slowly learning to speak to the universe using science instead of myth alone. The journey we have taken across the cosmos mirrors a journey inward. The same atoms that form stars also form the human body. The carbon in your cells was once inside ancient stars that exploded long before Earth existed. In this sense, you are not separate from the universe. You are made from its history. Technology may one day allow humanity to explore beyond our solar system. Future spacecraft might travel using advanced propulsion methods, or even use gravitational slingshots around massive planets to gain speed. Some scientists dream of interstellar civilizations traveling between stars, carrying life and knowledge across cosmic distances. Yet exploration is not only physical. It is also intellectual and emotional. Every scientific discovery expands humanity's understanding of existence. Every telescope image of distant galaxies reminds us that we are part of something much larger than ourselves. The universe is not just a place, It is a story unfolding across time. Philosophically, the cosmos raises questions about purpose. Some believe meaning comes from cosmic design. Others believe meaning is something that conscious beings create for themselves. In either case, the ability to experience the universe is itself extraordinary. The universe has created observers capable of studying its own structure. Perhaps the most comforting idea is that the universe is not rushing. Stars are born slowly. Planets form slowly. Evolution occurs slowly. Civilization itself developed gradually. The universe seems to prefer patience over haste. Even the expansion of space happens quietly, without noise or drama. As you reflect tonight, imagine standing under a dark sky filled with stars. Imagine knowing that each star is a distant sun with its own possible worlds. Imagine feeling the vast scale of space and time, yet also feeling connected to it. Because you are not outside the universe observing it, you are part of it, thinking about itself through you. The story of the solar system, the galaxy, and the universe is ultimately the story of transformation. Matter becomes stars. Stars become planets. Planets become life. Life becomes consciousness. Consciousness becomes curiosity. And curiosity drives us to keep exploring. The night sky is not empty. It is full of history, possibility, and future potential. Every star is a reminder that creation is still happening, still expanding, still writing new chapters in the cosmic story. And so our journey ends not with silence, but with awareness. The universe continues, and so do we, observers, explorers, and storytellers traveling through time and space on a small blue world beneath the endless night.